Hello everyone, this is Mrs. Lindsay Pereira. Today we're doing the second day of 1/6 regarding continuity. So let's take a look here. In this graph we are going to describe the places that the function is not continuous and explain which of the three conditions is violated. Okay, so if we're just going to go left to right, that's just how we read a book and read a graph. So I'm going to start going left to right. I'll move this down a little bit. Again, wherever I need to pick up my pencil, right here at x equals -2, that is my first area of not being continuous, or in other words, discontinuous. Okay? So if you recall, there are three reasons that you could have discontinuity. The function value doesn't exist, the limit doesn't exist, or they don't equal each other. Okay, so let's take a look at our graph here. Let's go back to our graph. All right, so what is going on here? Well, if you take a look at this graph here, it does have a function value. The function value at -2 would be 3. It also has a limit because both the left and the right-hand side are both going towards 1, so the limit is 1. So what is violated is the third one. The function value does not equal the limit at -2. Okay. All right, so let's move on to the next one. So now I come over here at x equals -1 would be the next one. Okay, because again, I have to pick up my pencil there. And I'm just going to go in order. This one, there actually could be a couple different reasons that it's not continuous, but I'll just go in the order. Is there a function value here? And there is not. So f of -1 does not exist, or is undefined, right? However you'd like that. Because, again, there is no closed circle. Over here, there was a closed circle. So let's move on to the next one. Keep going. And this, if you can kind of see from both directions here, that should be an asymptote right there. So at x equals 1 is our next area of discontinuity. Okay, so again, I'm just going to go in order here. Function value, there is no function value there. It never actually hits. So f of 1 does not exist either. Okay. All right, so let's move on to some more algebraic problems here. So we're looking here at 3. So again, we've got to take a look at this list here, and we got to go in order of first, what's the function value? Then we have to see the limit, and then they need to actually match in order for it to be continuous. So 1, we're going to do f of -5. So plug it in. And again, you're welcome to use your calculator here. Work it out by hand. Whatever you would like to do there, whatever's easier for you. Excuse me. Okay, and I'm actually going to talk about the bottom here because that's really the main area. Because if that's 0, this is undefined, and it actually is. So this is whatever that is up there, this is undefined. So right away, we know that this is discontinuous. Okay, so therefore, g of x is discontinuous at x equals -5. Okay, and again, the reason is there is no function value at f of -5. Okay, for the next one, I would actually like you guys to pause the video and try that on your own. Push play when you're ready to resume and check your answer. Okay, very similar to number 3. First thing you want to check is the function value, and because we have a fraction here, we really are concerned about the denominator, so I just focused on that first. And again, it's undefined, therefore it is discontinuous at x equals 1. Okay, so I want to talk a little bit, this is not in your notes, I have an example here about what is meant to be a removable discontinuity. Okay, a removable discontinuity. So I made up an example here. Okay, whenever you have examples like we just did, 3 and 4, when it's discontinuous, it is either a whole or an asymptote. A whole is considered removable, a removable discontinuity. So when do you have a whole versus an asymptote? Okay, so I just made up a problem here and I've kind of already worked it through. But if I have this problem and I factor it, okay, and again I'm going to refer back here real quick to 3 and 4. If I factor these, top and bottom, I would be able to determine whether or not, for in problem 4, if x is a whole or a vertical asymptote. And the same thing with -5. When is it a whole? It's when it cancels off. So if I had the numerator factored, the denominator factored, if it cancels off, that makes this value a removable discontinuity and therefore a whole. If it remains, that is a vertical asymptote. So x equals -5 in this case would be a vertical asymptote. X equals -1, which is a whole, which again is what we call a removable discontinuity. We can actually figure out what that ordered pair is supposed to be and where exactly we should draw an open circle. Well, again, if I cross this off, it reduces to x minus 1 over x plus 5, which is what I have right here. Okay, so again, I removed the whole, is essentially what I just did. To find out what that ordered pair should be for my removable whole, now I literally plug in -1 into my simplified equation. So when I plug in -1, I get a value -0.5. So that means my removable discontinuity is -1, -0.5. This is where the whole would be located on my graph. Okay? A vertical asymptote is not removable. Okay? So hopefully that makes a little bit of sense. You're going to see a couple questions in your homework talking about that. That's why I wanted to emphasize that just a little bit. Okay? All right. So let's now talk a little bit more about piecewise functions. We want to find all points where the function is discontinuous. So whenever you're talking about discontinuity with a piecewise function, again, what's really critical here is the point where they are actually changing from one equation to the next equation. Also, I do want to point out, too, these are both equal to at -1 and 5, so we're good to go there. If those were not equal to, we'd have to address that as well. Or if there was a space between here, we'd have to address that if this started at 3 and this went to 4, like our problem from the first day of notes. Okay? So in this case, we have to check to see if it's continuous or discontinuous at x equals 3. So again, we have to follow our guidelines there. We have to plug in f of 3, find the function value. Well, where does that apply? Doesn't go here because there's no equal, so it's going to be in our second equation. So that would be 14 minus 9, which will give us 5. Okay, so our first one's satisfied. We have a function value at 1. Now we have to find the limit as x approaches 3. Well, again, we have to check both the right and the left hand behaviors. Let me move this down. Well, we already found one of them. That's our work up here. We plugged it in where this bottom one is, and again, that's on the right side of it, so that would be our right end behavior. So I'm just going to rewrite our answer there as 5. Now I have to check the left-end behavior, and therefore that means I plug it into the top one. So 3 plus 2, that becomes 5. These match, so our limit is 5. So our function value is 5, and our limit is 5. So both of those are satisfied. Third step, does f of 3 equal the limit as x approaches 3 of f of x? So does this one equal this one? Sure does. So the answer is yes. Okay, so it is continuous throughout this domain. So there are no discontinuities. So it's continuous, though, only from -1 to +5. So therefore, f of x is continuous on the interval -1 to 5. Okay. And then let's move on to our last example here. This one's a little bit different, okay? Find a value for a so that it is continuous, okay? In order for them to be continuous, it's just like our previous problem. The function value and the limit should be the same, okay? In order for that to be true, we have to make sure our right and left end behaviors are the same. So again, we have to make sure that our right and left end behaviors are the same. So the limit of f of x as x approaches 4 from the right-hand side must match the left-hand side limit. All right, so this is our critical value, right? Which is, again, from the right and left-hand sides that we need to match. So we already know that's what our x is going to be here. Okay, we're going to plug in 4 for these x's. So my right-hand side is going to be x cubed, but instead of just putting x cubed here, I'm going to substitute in 4. So for my left-hand side, I have x squared plus x plus a, but again, I'm going to plug in 4 for my x's. So not x squared plus x plus a, I'm going to do 4 squared plus 4 plus a, and now I'm going to solve for a. Okay, so 4 cubed, 64, equals 16 plus 4. So that becomes 20. And then I can subtract 20 and get a to be 44. So that is your value. That will make it continuous. Okay? All right, so this concludes our notes for the second day of continuity.